Alright guys, so 4.6, we're going to talk about energy levels, and energy levels are the circles that we were putting around those diagrams. So when it says each energy level has a maximum number of electrons equal to, you heard me tell you guys a while back that circle 1, or energy level 1, can hold 2 electrons. The second energy level can hold 8, and the third energy level can hold 8. Now, I told you 8 for argument's sake, but this is how you figure out how many electrons each one can hold. Now, they go into this better, explaining it in Chapter 9. So we will kind of bounce around a little bit with the chapters here. But this is going to be each energy level has a maximum number of electrons equal to 2n squared. Alright, so what happens is where that n is, that's where you put in what energy level you're in. So if you're in energy level 1, that first circle, you're going to have something that looks like this. You're going to have 2 times 1 squared. Alright, and so 1 squared is 1 times 1, which is 1, and then multiply that by the 2, and that is going to be equal to 2. That's how I know that first energy level can hold 2 electrons. Now here is for energy level 2, I'm going to have 2, and then I'm going to square it. And 2 squared is 2 times 2, which is 4. And 4 times 2 is 8. Not 98, is 8. Which 8 electrons, right? Now, what we saw is that we were looking at energy level 3. We also said could hold 8 electrons. But if you do this math, you're going to have 3 squared. And 3 squared, 3 times 3 is 9, and 9 times 2 is 18. That up a little bit there. Alright, so energy level 3 can hold 18. Now, if I were to say energy level 4, 4 squared, 4 times 4 is 16. 16 times 2 is 32. Alright, so that's how many you can tell. Now, this is taking into account your transition metals. So, if we're ignoring that whole middle of the periodic table, then we know that we're just looking at 8 electrons, right? Our valence electrons they go up to 8. So valence electrons, talking about that. They determine chemical properties of an element, right? The valence electrons are going to decide whether something wants to react or not, if something's happy. And if they're not happy, then you'll see like kabooms. And it doesn't have to be a big kaboom. It could be, oh, look, it made a solid. I poured 2 liquids together and it made a solid. Or, hey, I poured 2 liquids together and you see some bubbles. Nothing crazy, but you see a few bubbles. So it's just, they're going to react. Or, hey, I poured 2 things together and they change colors. Electrons, valence electrons are the electrons in the highest energy level, so the electrons in that outer shell, or that outer circle. They are the same as the group number of the element. So remember, group number are in columns. Example, phosphorus has blank number of valence electrons, so let's look here. Phosphorus is right here, it's going to have 5. So what I would do if I were you guys, on your own periodic table, I would put 1 VE, 2 VE, skip this whole middle section, 3 VE, 4, 5, 6, 7, and 8 VE for valence electrons. So phosphorus has 5 valence electrons. So put that here. Alright, so now the learning check says, state the number of valence electrons for each. Now, I know that we just said, hey, energy level 3 can have 18 valence electrons. But that is because they are looking at the transition metals here. Alright, so if you look at energy level 1, 2, 3, they're going to take into account, I know it says 3, and there's 3 here, and it looks like nothing here. This is why I don't like the way this book is written. Because, yeah, if you look right here, it looks like, oh, energy level 3, period 3. 1, 2, 3, 4, 5, 6, 7, 8. but you are also counting these 10 right here that are really look like they're in period 4. That's where you get your 18 from. Now in chapter 9, we will learn why, and even though it's not up here in period 3, it's down here in period 4, why we count those. But it's all about the energy levels and how much energy these elements have. So anyways, we'll discuss that a little bit more. But for right now, know that we are skipping these transition metals, and we're skipping this whole section here, which we will learn about in chapter 9. And we're just counting these, not transition metals, we're counting these representative elements. So 1, 2, 3, 4, 5, 6, 7, 8. Alright, so state the number of valence electrons. So for oxygen, we're right here. If you look above, it's going to be 6, or you could just count over 1, 2, 3, 4, 5, 6. So the answer for this is going to be 6 valence electrons. Aluminum. If you look at aluminum here, it's going to be 3. Chlorine, 7. See if it's going to let me. The first time I did these notes, the ones that you guys could not see, it would not let me highlight this number 7. Don't know why it won't let me, but it will not let me. The answer is 7 though, okay? Calcium is going to be 2. I believe this one, yeah, that one did let me. Alright. Group 6A, so everything in 6A, which is right here, is going to have 6 valence electrons. And then carbon is right here. That's going to have 4 valence electrons. Alright, now the electron dot models we have done, so this shouldn't be anything new to us, but it shows the valence electrons around the symbol of the element. You're going to place dots above, below, or on either side of the element. Now, this is not where electrons are found in true, like, nature, but this makes it easier for us. So go ahead and you'll do top, bottom, side to side for your dots. Dots pair up, but not until they're on all sides of the symbol. So look at this. Hydrogen, lithium. Now go over to beryllium, boron, carbon. You got top, side, bottom, side, and then nitrogen, you start to pair up. Oxygen, you have 2 pairs. Fluorine, you have 3 pairs. And then finally you get to the end here, and you have your pairs all together here. Alright? So that's the electron dots, and we've done several of those. So we're going to write the Lewis dot structure for bromine. So I'm going to do a text box. I'm going to go ahead and put BR. And then I'm going to put my dots around it. So let me make these, I'm going to try to make the dots a little bit smaller here. Alright, so for bromine, if you look at this periodic table, it has 7 valence electrons. So I'm going to put dots around it, but I'm going to go 1, 2, 3, 4. Now I'm going to go back and pair up. 5, 6, 7. Alright, so that is my Lewis structure for bromine. Now, ionization energy, that is how hard is it to remove an electron. So the harder to remove an electron, the higher the energy. So I always do it this way. When I'm standing in class, I'll say, okay, when I'm standing by the board, who could I hold on to if I wanted? And if you're in 3rd hour, then it's going to be Carter and Grayson and Sierra. Like, I can grab onto those. I can hold on to those students. I can control them. Now, the back students, say like Lucy and Kylie and Andre and Emma and Carlin, like all those are going to be the hardest for me to control. It's the same thing for an element. If you have a bunch of different circles or energy levels, that first energy level is going to be easiest for that element to kind of control those electrons. The further you get out, the more circles or levels you have, the harder it is, and the more those electrons are more free to come and go. So another one would be, who could easily, get away from me if I'm staying at the board. That's what I just talked about. So same thing with these electrons. Electrons that have got more energy levels, they're going to be easier. It's going to be easier for them to lose electrons. Alright, so if I'm looking at this, it's going to be easier to lose an electron from potassium than it is going to be from hydrogen. And then also, as I go across the periodic table this way, argon, these are my noble gases. They are happy. They don't want to react. They like being by themselves. So they're happy. They're not going to lose electrons very easily. So they have high ionization energies. So helium would be like one of my highest ionization energies. So as I go up the periodic table and as I go to the right, my ionization energy is going to increase. Alright, so I'm going to draw the Lewis dot diagram for, let's see here, for lithium and for sodium. Okay, so for lithium is Li, for sodium, Na. But if you look at lithium and sodium here, guys, lithium and sodium, both one valence electron. So I'm just going to do the one. I'm just going to put it on top. It doesn't matter where you put it. I'm just putting mine on top. I always start at the top for some reason. Alright, now, they both have one valence electron, but if you use that method, sodium's going to be able to lose that electron a little bit easier than lithium. Now, lithium, it'll also want to lose that one electron, but it will be easier for sodium as far as how much energy it needs to be able to do that. Alright, so I'm going to draw a Lewis dot diagram for lithium and fluorine. So I know lithium has one, but look at fluorine. It has 7 valence electrons. Alright, so let's draw lithium. Of course. So there's lithium. I'm going to do fluorine right there. And then let me do my dots. I'm going to make them a little bit, tiny bit bigger here. So lithium, I'm going to put it onto the side here for what I want to do. There's 1. Fluorine's got 7, so 1, 2, 3, 4, 5, 6, 7. So you can look at fluorine. Now, the magic number here is going to be 8. So you can see that, hey, lithium has 1. It's not really all that happy because it has 1. Fluorine's not all that happy because it has 7. It's not in this perfect, like, world. So, I have to move. So you can see where maybe, just maybe, these two could make each other happy. Alright, so we're going to start looking at that. That's the end of Chapter 4 notes. Chapter 5 will get into this. How do we know what is going to bond with each other? Alright, if you guys have any questions, let me know. And I will hopefully see you soon.